let me introduce you to the graphical method of doing convolution. So this is graphical convolution done graphically, and we're going to call it the flip and slide method. Just like the way we took partial fraction decompositions was the cover-up method. And I'm going to start you out. It's like so many things, it's easiest by example. So I'm going to give you an example, the same one we just did, where x of t is this decaying exponential, and our h of t is an impulse. So the way to do it is to first I'm going to first just remind everybody what the definition is. And our convolution definition is that our output, our convolution of our input with our impulse response, is equal to the integral of x of tau h of t minus tau d tau. And this is what we're going to do just with pictures. So our first step is to plot x of tau. I mean, just realize we're just plotting the first part of our integral. So there's our plot of x of tau, and the only difference is that we just changed our independent variable from t to tau. Then the second step is you're going to plot h of minus tau. So we're going to start by evaluating this part. And I got to choose some value for t, so I'm going to start off by assuming that t is equal to 0. And when you plot h of minus tau, that's just the same thing as you're going to flip h of tau. So that's the reason why we call it the flip part of the flip and slide. So we flip this thing around and we get this.
So are you assuming that t equals 0, or are you just assuming that that function changes at 0?
We're going to assume just for now that t is equal to 0. And we have to assume something because when we want to evaluate this integral graphically, we've got too many variables. We've got both a t and a tau, and we need to keep our tau variable as a variable. So we just have to start somewhere.
So I understand why you'd be assuming then, because wouldn't where that unit function changes to whatever it's going up to be determined by u of t minus 5 or u of t? Like if u of t would change at 0, so it's 0 until 0, and then it goes up to whatever value in front of the u of t. And then u of t minus 5 would change at t equals 5, right? I don't understand why you have to.
Yeah. No, I think I understand what you're saying, and I think that this will answer it. We're going to do this a bunch of times. And we're going to start finding what is y of 0. What's our output at time equals 0? We're going to peg t to be 0 to find out just a single value of our output. And to find our output at y of t equals 0, anytime you see a t in here, we will replace it with 0. And so I think I'm answering your question. The way I'm going to start off doing it is evaluating this thing for t equals 0. In order to do that, since I see two things multiplied together, I'm firstly going to graph the thing in red in here as red. And then the second thing is I'm going to graph the thing in green here for t equals 0 in green. And for t equals 0, h of negative tau is in fact this. And then I'm going to multiply them together. And then when I multiply them together, I'm going to both multiply and I'm going to integrate to find y of 0. Let me make that even clearer. To find y of t equals 0. So when I multiply them together, I'll do that same piecewise thing. 0 times 1, 0 times 1, 0 times 1. That's all going to be 0. And then all of a sudden over here, I get stuff over here, but it's all times 0. So I'm going to get 0 everywhere. And what I've just graphed here is the product of x of tau times h of 0 minus tau. I've just graphed everything inside this integral sign. And so now I'm going to do the integral. And Aiden, what is the integral of that?
0.
0. So therefore, the integral is 0. So therefore, y of 0 equals 0. Did I answer your question?
I guess I'm just more less understanding why we're doing at t equals 0 if it's for all time negative infinity to positive infinity.
We're not doing x of 0. We're doing t equals 0. And we have to start somewhere. But now that we found y of 0 equals 0, we're going to do it for a different place. Now we're going to do the same thing again. But instead of all this being y equals 0, let's do it for y equals 1. And then let's do it again for y equals 2. And eventually, when we have a whole bunch of different things, we'll be able to get some intuition for what our result looks like. So far, what we found is our graph of y of t versus t. This entire integral that we did early on just shows this point, that y of 0 is 0. So now let's do this next one. We have to do a whole integral for every single spot on this graph. The next spot is we don't need to replot x of t, x of tau. We're just going to reevaluate this now for a new t, the whole thing. We don't need to replot this first one, though, because it's the same. It hasn't changed. The first one still looks exactly like it did before. But now, John Enger, what is our new green thing when we're doing it for y equals 1? Shoot. I think I see the problem. I wrote this incorrectly. What I should have said all along is that we're doing this entire first section for t equals 0. This is going to be for t equals 1. This is going to be for t equals 2. Aiden, does that clarify it or still not?
I believe you're asking Dom, sir, but
oh, Dom, I'm sorry.
Yes, that does.
So just you're gonna do this for several points. So at t equals 1, you'll do h of t minus or h of 1 minus tau plus the area underneath that curve plus the area underneath x of 1, and then you just do that for several points.
That's it. And in the limit infinity, but I think we can probably get a feeling for what it looks like before we go through an infinity.
Okay,
So
I just didn't understand. Sorry, go ahead.
I'm sorry, I misunderstood your hearing. You're the person by your voice sound. So John, again, tell me, what does h of 1 minus tau look like? When does that shoot up? When does it go down?
It would go down at 1 or tau.
It goes down at 1. Yep, that's right. When tau equals 1.
So just be a step function right there.
It comes down. So when you call it the flip and slide, this is the slide thing. We just took our h, we flipped it, and now we've slid it to the right. And so now we'll do the element by element multiplication. And we can see that now there is a small area where they're both, I did not do a great job of lining up these axes. That's better. Now we can see that they're to the left. We're still getting all zeros because our x of tau is 0. But now to the right, there is this region where this is 1 times this. So now it looks kind of like this before it instantly cuts off. And now we're going to do the integral of this. Kind of hard to see, but what we can make the argument that since this is 1 and this is 1, we know it's less than the 1 by 1 unit square. So it's going to go up by quite a bit. We're just not sure exactly. Since we're doing it graphically, we're not quite sure how much. We know it's less than 1. We know it's popped up to here. And now we'll do it again for t equals 2. And for t equals 2, I'm not going to redraw everything because x of t, the first part, stays the same. The second part, we've just pushed this thing even further over. And now with this thing further over, now maybe it's clear that when we multiply them together, we're going to get something that looks like even more of an exponential down to maybe here. And it will have increased, that area will have increased, not as much, but by some. And as we add, and as t gets bigger and bigger, we'll add more and more, but not as much. And eventually, it'll even out for some large t, that is just simply the area underneath this curve. And what is it for negative t? If we shift this guy further to the left, Sabine, what happens? What's our y of t as we shift this green curve to the left?
Wouldn't it just be its reciprocal?
Let's try it. Let's try t equals -1. So I'm going to graph the entire thing. We've got our x of tau, which never changes. We've got our h of, now it's going to be -1 minus tau.
So, sir, is it not going to add anything because there's nothing to the left of it?
That's what's going to happen. We're going to have, it's going to now pop up over here at -1. So when we multiply these guys together, we're just going to get 0 everywhere. It's going to be 0 out here because this is 0. It's going to be 0 in here and everywhere else because that's 0. So therefore, for time greater than 0, for time less than 0, our y of time less than 0 is going to have to be equal to 0 because there's, when we integrate it, there's no space under there. And so this intuitively gives us a graphical explanation about why the integral from -infinity to +infinity of x of tau, which is e to the minus tau u of tau, times u of t minus tau d tau. That's just what we've done down here for multiple different versions of t. And it tells us why it's equal to 1 minus e to the minus t u of t graphically. So we've solved it 3 different ways. We've solved it using exactly using math. We've solved it approximately using Laplace, and we've solved it using graphical convolution. At the end of this class, what I want you to be able to do is definitely know how to do convolution by math. You already should know how to do it using Laplace, and you should have a rough idea about how graphical convolution works, but you can't back out from this picture, but you should have a rough idea about how to do graphical convolution. I don't care if you don't have the graphical part. Perfect. You will get graphical convolution perfectly. That will be necessary, but we'll do it again in a future lesson. Any questions for me before we go?